Hello and welcome back, everybody. Taking a look at Chapter 4, Section 2, Reaction Types, and we're taking a look now at solubilities within the different precipitate reactions. Okay, we're still in precipitate reactions, but now taking a look at something a little bit different in terms of those precipitates. And there's a bunch of different rules that technically you're not supposed to have memorized, but you're supposed to have these memorized. And I'll explain more with that. AP College Board does not provide these set of rules of what's soluble and what's insoluble, what's going to form a precipitate. However, they did assure us that the examples of things that are going to be precipitating out are going to be pretty obvious to students. So I guess the biggest thing at this point is, what does all of that mean of what I just said between soluble and insoluble? Okay, so a precipitate reaction really means I guess I should back up that I usually label these things as a precipitate. These are going to be our solids when we mix them in. So if I have a solution, I'll go back to the example I gave the last unit. If I have a solid in here, say it's something like sodium chloride, okay, and I have my liquid, that's going to be my solvent. If this will actually dissolve, it'll become soluble in that the water molecules will pull away or dissociate these solids. Okay, that would be what we call soluble. Now, there's a symbol that we use for this. If it is soluble, that means it dissolves, and that means that it is going to be found in an aqueous state. Okay, if it's solid, if it's insoluble, that means it's going to be a solid, and that will form the precipitate. And so what we're seeing in front of us is just a bunch of rules that will actually go through and say, when is something going to be soluble? When is it going to be insoluble? Remember that these are all going to be the metals that are involved in this. So that means it's going to be ionic compounds that separate into their ions. So basically, when we say most, all nitrate salts are going to be soluble. So anything with nitrate is going to be soluble. It's going to be aqueous. If we have something that alkali metals, now remember, alkali metals are column 1. And so here I've got some examples. And also something that involves the ammonium ion. That's NH4 plus 1. So that's going to be the thing that's going to be soluble. Again, aqueous with these. So column 1 with the column 17, we're going to be finding those going to be aqueous. Now, most of those column 17s are going to be soluble. It's kind of a redundant step, but there are some that are not. And so if we have silver chloride, lead 2 chloride, and this one is kind of a weird one. This one's mercury chloride, and so on. If you see mercury, lead, or silver, it's not going to it's not going to be dissolved. And so an example that we'll see quite often come up is something like silver bromide. That would be solid in nature, doesn't dissolve. Okay, so that's one of those exceptions to the rule. Most of the sulfate salts, that remember sulfate is SO4, -2, and some exceptions of that are going to be barium. There's my lead again, and there's my mercury again. So what do we know? If I see silver, if I see lead, if I see mercury, if I see barium, those are ones to get on your radar. They're going to form solids. Here's another one. Hydroxides are only slightly soluble. There are some soluble hydroxides that we'd find. That's going to be potassium and sodium hydroxide. Only these guys, these are kind of tricky ones. They're only marginally soluble. I don't think you can run into too many problems with that. We'll deal with that in turn. Then we've got some other ones that are only slightly soluble. In fact, we almost always call them insoluble along the way. Most sulfides, carbonates, chromates, and phosphates. Okay, so that's basically just using those. We'll keep referring back to them as we go. And so your big question right now is, okay, so why does this matter? Okay, we're going to be going through some problems and taking a look at how does this all work. If we're going to be taking a look at some reactions going on. So you'll notice we're only giving you half of the reaction. We have to be able to annotate everything along the way and predict what the products are going to be. This is like a double replacement reaction. So let's convert everything into symbols. Now, this Roman numeral 2 means it's a +2 charge. Nitrate is an NO3 with a -1 charge. And then I have potassium iodide. Potassium's in column 1, iodide's in column 17, so it's a +1 and a -1. So they're going to swap partners, and my lead and my iodine are going to swap, My lead, remember, had a 2. My iodine had a -1, so that's a PbI2. And then I have my potassium with my nitrate. My potassium was a +1. My nitrate is a -1. Okay, so now that's all taken care of. Now let's balance. I have 2 nitrates over here, so I put 2 here. That gives me 2 potassiums. That gives me 2 potassiums here. Now distribute the 2 to your iodine. Oh, I've already got that, and I've got 1 lead. Problem's done. Okay, so that's just balancing those equations. Okay, that's all the prompt was asking you to do on this one, so you don't have to apply your solubility rules. Don't do more work than it asks. Now it says to complete the ion equation. Okay, and I'm going to put up the next prompt of putting the net ionic equation. So what we had, if I can remember this right, we had ourselves a PbNO32 plus 2 Ki's. That's going to give me a PbI2 plus 2 of my potassium nitrates. Okay, now I go through and I can assign my solubility rules. Most nitrates are going to be soluble. My iodine, this is a column 1 and a column 17, that's soluble. And my nitrates are soluble. And this guy, because it contained that lead with a column 17, is a solid. Now we apply it because we're going to do an ion equation. Okay, that's going to build into the net ionic equation. So what this means, by ion equation means we're going to split up everything that's aqueous only. So if it's a solid, a liquid, or a gas, it never dissociates. So let's split up everything into their ions, kind of working everything in reverse. Now here, be disciplined, please. Make sure you include the states of matter, and that's going to save us a lot of problems later on. Okay? I'm not going to worry about that coefficient out in front because we're going to have to balance from there later. You can include it, but I'm going to show you what we're going to be doing with the net ionic equation. So we're going to get, now remember, your lead iodine does not split up because it's a solid. That means it has an overall charge of 0 because it's neutral. And then I have my potassium ion, that's aqueous, and then my nitrate ion, that's aqueous. Okay, now comes the fun next step. The next step to get down to the net ionic equation is basically asking what's important out of all of this. Okay, what I mean by important is what's exactly the same on both sides and what's different. Well, if I look on this, I see that my nitrate is exactly the same on both sides. I see that my lead is different. Oh, there's my potassium. That's exactly the same on both sides. So essentially, when I go down into the net ionic equation, I'm going to eliminate what's called the spectator ions. Spectators are those people that are in the stands that are watching a sport go on. The reality is they don't really matter. So what we're saying in terms of chemistry is the nitrate really isn't important in this equation, nor is the potassium. Instead, what we see is that my lead is important in this reaction, and my iodine is important. Now notice that these are ions. They're important in the reaction to get my precipitate of lead to iodine. Okay, now the next step with this, now that I've done the net ionic equation, the next step is to balance my charges. Notice on this side of the products, that's 0. On this side, it's a +1. Now, the rule is to balance the charges. This doesn't mean both sides have to equal 0. So if you have leftover stuff that's here, that's fine. We just have to get the ions on one side equal to the ions on the other side. So to balance the ion charge, I have a +2. Now I have a -2. +2, -2 is 0. There's 0. And my elements is the third component. If you balance charges first, then that usually cleans it up. Notice I didn't just automatically carry that 2 down because that can throw things off. There is my net ionic equation. Okay, so it's just a matter of going through the steps. To do the net ionic, you do the complete ion equation. You actually identify your spectators and cancel those out. And the net ionic equation, it just goes through the important stuff behind it, if you will. Okay, so let's take a look now at some of the other questions that come up with it. Okay, let's do the exact same thing for copper 2 sulfate and sodium hydroxide, as well as potassium nitrate and barium chloride. All right, so let's take a look. First of all, let's do copper 2 sulfate. Copper 2 sulfate as CuSO4. The Roman numeral 2 balances out the 2 of that. Using my chart, I see that's aqueous. I see sodium hydroxide, +1 charge. Hydroxide is a -1 charge. That's aqueous. And then I'm going to get, in a double replacement, I'm going to get copper hydroxide. Hydroxides are tricky. That's going to be my solid. There's only a couple hydroxides that are soluble. And then the other one is going to be sodium sulfate. Now notice the 2 shows up because the charge on sulfate is a -2. The charge on sodium is just a +1. Similar, there's a charge on hydroxide of 1 that goes here, and the charge of the copper goes over to my hydroxide. This guy is soluble as well. Okay, so if I want to do the next step of ion equation, let's split up everything that's aqueous. This is a 2+, that's aqueous. This is a sulfate, that's a -2, that's aqueous. This is a sodium, that's aqueous. And here's my hydroxide, that's aqueous. Now, my copper hydroxide is a solid. It does not dissociate. Solids, liquids, gases do not dissociate. They have an overall 0 charge. Sodium is a +1, that's aqueous. And my sulfate is a -2, that's aqueous. Who are my spectators? Who's exactly the same on both sides? That would be my sodium. That would be my sulfate. Net ionic from this, rewrite it, keep it clean. Copper as aqueous plus hydroxide, that's aqueous. And that's going to give me my copper hydroxide. That's a solid. And overall 0 charge, and there's nothing else remaining. Balance the charges. Looks like I need 2 of these. +2, -2, and 0. 1 hydroxide, 2 hydroxides. Oh, I'm going to need to do that, aren't I? Oh, wait. I'm sorry. I missed the 2 there. Never mind. We don't need that. We're balanced. All right. So notice that I made that mistake. You got to carry everything in there as it is. Now let's take a look at that last one, and let's try to speed up the process. I can't speed up the first step. I see potassium nitrate, and that's aqueous. And I have barium chloride. That's aqueous. Okay? Now that's going to form my potassium chloride. That's aqueous. And I'm going to get barium nitrate. And that's a 2. Okay, now when we take a look at that, I see everything is aqueous in here. And so really there's going to be no reaction. The reason is there are no spectators. Or I'm sorry, they're all spectators. Not no spectators, they're all spectators. They're all exactly the same on both sides. Now, what I was alluding to when I said, let's speed up the process, I don't necessarily have to do the complete ion equation every single time. I can just kind of eyeball it and say, okay, this nitrate is aqueous, this one's aqueous. I could just do that mentally, and I could say potassium and potassium, chloride and chloride. But I don't need to do this necessarily every single time to complete the equation, identify those. I could probably jump down to just doing a net ionic by isolating those things that make my solid. In this case, since everything was aqueous, it's not going to be a reaction at all because everything ended up being canceled out. Okay, so just taking a look at an example like that. Now let's take a look at how this all works in terms of stoichiometry. Okay, we can do some things with the stoichiometry that we did in Unit 3 and see how this would apply. And guys, this is simple. This is just stoich. It's nothing extra off of any of this. So don't worry when we say precipitate stoichiometry and everything. It's just reminding how this works. So let's take a look. We've got sodium chloride that's going to be reacting to silver nitrate solution. Okay, so first of all, let's write a balanced equation. Okay, so I have sodium chloride, that's going to be aqueous, and I'm going to react it with silver nitrate. All nitrates are soluble, so that's aqueous. Okay, so that's going to be making silver chloride. Okay, now notice that's going to be a solid, and I'm going to be also getting sodium nitrate, and that's aqueous. So that's the first step, just write. And now we should just kind of move forward and let's maybe balance the equation. 1 sodium, 1 sodium, 1 nitrate, 1 nitrate, 1 silver, 1 silver, 1 chlorine, 1 chlorine. Cool, we're balanced. All right, so it's a balanced equation. Now the process is saying that I have, in this case, let me see, we have 1.50 liters of a specific molarity of solution. All right, so we want to know we're adding 1.50 liters of a 0.100 molar solution. Remember, molarity is moles of solute over liters of solution. What does that mean? We go back to our equation. 1.00 equals X moles, and in this case, it's going to be adding it to a certain amount of my silver silver nitrate solution. So we're talking about the solution here of silver nitrate, and we're adding it to 1.5 liters of solution. So my X, what I'm really getting is I have 0.15 moles of silver nitrate. That's how much silver nitrate I have present. Now the problem becomes exactly what we know with our stoichiometry. Okay, I know that I have this many moles. Let's convert 1 mole of silver nitrate. And the question is asking my sodium chloride. So let's convert from my silver nitrate now into my moles of sodium chloride. Now I can go 1 mole of sodium chloride is 58.5 grams of sodium chloride. Okay, periodic table, look at the masses. All right, so what that gives me is a mass of 8.77 grams of sodium chloride. That's it. So I just found, with this concentration of silver nitrate, I know now how much sodium chloride I could get. But the next part of this question is asking something a little bit different. Okay, so let's take a look at that one. If I can wake this up again. And it's not getting there. All right, now we're ready to roll. Now let's ask, what happens if I use barium chloride instead? All right, so let's use it instead to precipitate out those silver ions. So instead of my sodium chloride, I'm going to use barium chloride. And barium chloride is aqueous. And I'm going to add that to my silver nitrate solution. That was aqueous. And I'm going to get barium nitrate. That's going to be my solid. That's precipitating out. Oh, I'm sorry. This is aqueous because it's your barium nitrate. All nitrates are soluble, excuse me. And my silver is going to be precipitating out. Okay. Now let's balance. I have 1 barium. I have 1 barium. I have 2 chlorines. Let's get 2 chlorines. I have 1 silver. I have 2. Oh, I need 2 here. And I have 2 nitrates. 2 nitrates. I'm good to go now. All right. So the question is, what would I need to precipitate out if I use barium chloride instead? Well, remember, with this, I had my molarity is moles over liters, and so I had 0.100 moles equals X over 1.5 liters. Okay, so what that gave me, just to follow up with the math with this, is, let's see, I'm going to go and forgot what I had in there. Oh, I had 0.15 moles of silver nitrate. Okay, that's just what that X was. Okay, so let's take that 0.15 moles of silver nitrate and let's convert that now back to barium chloride. How much did we need? Remember, that's what the question was asking. And so I see that now with my balanced equation, I had for every 2 moles of my silver nitrate, I got 1 mole of barium chloride. Okay, then I convert my barium chloride, 1 mole of barium chloride ended up being 208 grams of barium chloride. All right, so what I get there is 15.6 grams of barium chloride needed. whereas with the last problem, I needed 8.77. Reason for that is obviously the formula mass is different, but also my mole ratios are different. Okay, so that's all we're doing with precipitate stoichiometry along the way. And we got a strength of solution in there. So that's taking care of that. And let's now take a look at a different scenario where we've got, in this case, a solution of sodium sulfate and solution of lead nitrate are mixed together. So that means we're putting in two things here. Okay, we're putting in my lead solution. And so my lead solution is a 0.0500 strength, and we have 1.25 liters worth. But my sodium solution is a 0.0250 strength, and it's a 2.0 liter solution. So I'm going to end up with like 3.25 liters total, aren't I? So let's take a look at what's going on to figure out the mass of precipitate formed. So it's a stoich problem with this. Let's balance an equation. I take a look at sodium sulfate, Na2SO4. That's going to be aqueous. We got to figure out who my precipitate is, don't we? We have to take a look at my lead nitrate. Now, all nitrates are soluble pretty much, so that's going to be aqueous. And so let's take a look at my lead sulfate now that's being formed because we're swapping partners. And I see my lead is actually a 2 charge, and so that would cancel out the 2 of my sulfate. All right, so that's going to be my solid here, and then I end up with 2 NaNO3s, 2 sodium nitrates, and that's going to be aqueous. Okay, and I put a 2 out in front because I had a 2 here. I have a 2 in front of here because I have two leads. Now that means I've got 2 sulfates. I've got 2 sulfates. That gives me 4 of my nitrates, are my sodiums. And, oh, that takes care of that. So notice I kind of balanced it out. Just kind of start with things and you might have to adjust. Okay, so let's take a look. Now, with this, notice here's my precipitate. That's what I want to solve for. I want to know how many grams of this. All right, and just looking at the problem, my nitrate is going to be a spectator. That's gone. And it also looks like my sodium's going to be gone. So my net ionic equation is really sulfate, that's aqueous, and my lead, that's aqueous, and that's going to make my lead sulfate. That's going to be my solid with an overall 0 charge. Now notice it's a 1 to 1 to 1 ratio, isn't it? Okay, so what we end up with in this particular case is 2 solutions. Let's figure out our strengths, and notice it's a 1 to 1 ratio with everything. So let's figure out these things and let's track it. Now I have concentrations of solution. So let's take a look at my my sulfate solution. We saw that that was a 0.0250 mole solution. Okay, that's going to equal 0.0250 moles over 1 liter, but I don't have 1 liter. Notice I'm taking a little bit different approach to this so you guys can figure out which way it works best. I had 2 liters of the solution, which means that I have a 0.05 moles of my sodium sulfate. Okay, now let's do that simultaneously with my lead solution. Okay, now with this, I had a 0.500 molar solution. That means I have a 0.500 moles over 1 liter. And notice with that solution, I had 1.25 liters, didn't I? Okay, so that's going to give me a 0.625 moles of my lead nitrate. Now, notice I switched techniques. I didn't just go M equals moles over liters and plug in values and solve for X and do that. I can do that this way. You choose which way works best for you. I'm going to use this technique from here on out. Now, we took care of how many moles are in there. Now let's convert then my sodium sulfate. Let's convert that moles into my sodium into my moles of my, and notice that the sodium sulfate into my moles of my, in this case, we're going to lead sulfate, my solid. Okay. Now notice here, it was a 1-to-1 ratio. Up here, it was a 2-to-2 ratio. You're good either way. Okay. It's going to cancel out mathematically. So then 1 mole of this gives me 106.9 grams. No, I'm sorry. That ends up being a 303.2 grams of lead sulfate versus, okay, let's take a look at my lead nitrate in here. That ended up being a 1-to-1 ratio there, which works because that's a 2-to-2 ratio up here. Okay, so 1 mole of my lead nitrate to 1 mole of my lead sulfate. So that ends up being, oh, and then I got to convert that into grams. 1 mole ends up being 303.2 grams of lead sulfate. And so calculator work, I see this ends up being 15.2 grams versus 189.2 grams. Well, what does that mean? That means that I only get this. I ran out of my sodium sulfate. This is what I call my limiting reagent. I have way more lead nitrate than I needed. That's my excess reagent. Okay, so that's how we do that type of problem. Straight up stoic, but it's just kind of walking through, figuring out, first of all, who is my precipitate, and then just keeping track of things along the way. All right, let's do one more piece, and that will finish us up then for this unit. We're taking a look at a precipitate produced when we have 35 milliliters of a lead iron 3 nitrate and mixed with the 55 milliliters of your potassium hydroxide. So let's go back, switch to a pen. We have iron 3 nitrate, and that's aqueous. And we're going to mix that with potassium hydroxide, that's aqueous. And we're going to get potassium nitrate, that's aqueous, because all nitrates are aqueous. And we're going to get iron 3 hydroxide. That's my solid. There's my precipitate right there. All right, so we're going to be mixing this in. Let's keep track. Notice that my nitrate really isn't valuable here, and my potassium really isn't valuable here. It's really about my iron, and it's really about my hydroxide. Okay, so let's take a look at these solutions. We'll take them in turn. Let's deal with my iron part first, just because it's listed first. All right, I have a 0.250 molar solution. That equals that many moles of my iron over 1 liter, but I don't have a liter. I have 0.035 liters. Okay, so if I do that, I'm going to end up with, do I have 3.5 or 5.5? I have 3.5 on there. Okay, so that ends up with, hopefully I did my math right here, a 0.00875 moles of my iron nitrate. Okay, so then we take a look, and I've got my hydroxide that we're tracking, and we started with 0.18 molar, which means I have that many moles of my hydroxide per liter, but I don't have a liter, do I? I have a 0.055 liters of solution. That gives me a 0.0099 moles of, let's see, my iron hydroxide. Nope, of my potassium hydroxide. That's what we started with. All right, so now we've got it all set in place. Let's look at our equation. Let's see, I'm balanced, 1 nitrate. Oh, I've got 3 nitrates, because 3 nitrates here. That gives me 3 potassiums, 3 potassiums, 3 hydroxides, 1 iron, good to go. Now let's go from moles of my iron nitrate. I saw I had 1 of those, 1 mole of iron nitrate, to my precipitate, which is 1 mole of my iron hydroxide. And so I end up with that. I end up with 0.93. Oh, nope. I got to finish off one more thing, don't I? I got to go 1 mole of my iron hydroxide into grams. You can stop in the mole, but why? If we're going to be going through, we want to know what mass, might as well finish it off in entirety. Then you just circle your smallest answer. So that ends up being 106.9 grams of iron 3 hydroxide. Okay, if I do that step, then I end up with 0.935 grams. Okay, now let's follow my potassium hydroxide with it. I see that it is a 3-to-1 ratio. That means I have 3 moles of potassium hydroxide to 1 mole of my iron hydroxide. And so then I do that last same step, 1 mole iron hydroxide into 106.9 grams of iron 3 hydroxide. Okay, so that will end up giving me only 0.352 grams of iron 3 hydroxide. You always should label. I know it's a time-consuming step in there, but we want to make sure we do all those things. This then would be my limiting. This would be my excess reagent. You don't have to label that, but that helps to figure out those next steps. Okay, so that will carry us through those types of problems along the way. It is kind of putsy work because it has all the different steps to it, but in keeping track of those things, you should be able to do the problems. We're going to be taking a look at some precipitate problems, some practice problems, some take-home quizzes, and up next, that will conclude our different parts of the precipitates for those reactions, and that will bring us up into the next type, which is redox, which is in section 3. Good luck.